How's everyone doing? How's everyone doing? All right. You ready to talk about the future? All right, let's do it. Facebook's mission is to make the world more open and connected. And most of you experience this mission every day in our products, things like Facebook, Instagram, WhatsApp, and Messenger. But I wanted to spend this morning talking about the future, talking about our 10-year vision and the most important problems we are trying to solve for the future. And that 10-year vision falls into three major buckets. The first is connecting the billions of people around the world who don't have access to the internet. The second is building truly intelligent machines that can help all of us manage the mass of information we have online. And the third is building truly rich, immersive, virtual reality experiences that let us experience anything with anyone at any time. Connectivity has happened so quickly for everyone in this room, it's hard to remember a time when we weren't running around with a supercomputer in our pocket. But if you look back at even just recent events, in 2005, the election of Pope Benedict, the same event 8 years later with the election of Pope Francis, notice the difference? Everyone is running around now with these high-speed computers and high-speed internet access. And so it allows us to build applications we could have never dreamed of even years before, like the idea that any one of you at any instant can become an HD video broadcaster, broadcasting what you see to the entire internet live in the moment. So when world events happen, like the recent attempted coup in Turkey, you can see this event through the perspective of all of the people on the ground watching it happen. So the next 10 years is about bringing the 4.1 billion people around the world who don't have internet access, bringing their voice to the internet so they can join us in this conversation. And to do that, we need to implement solutions that work in all the different ways in which people live. In very rural environments, we need to go to space. For suburban areas where we need higher bandwidth, we think high-altitude solutions work. And in urban environments, the key is wireless solutions for high-speed, local backbone without having to dig up the streets to lay cables. Now, these are big bets, 10-year visions, and you don't make big bets unless you have big failures. And at our scale, this is what failure looks like. This is the Amos 6 satellite, several days before launch, designed to provide internet access for much of sub-Saharan Africa. Let's take a look at what happened. Not supposed to do that. And in case you think we could recover the payload, that's actually the satellite right there falling, and it's definitely gone. So that's a bummer. That's going to set back our work in space for a little bit. But this is why we take multiple approaches. And the good news is our work in upper atmospheric solutions are making rapid progress. This is Aquila. It is a high-altitude, long-endurance airplane made out of carbon fiber, powered purely by the sun, by solar-powered, has the wingspan of a 737, weighs less than 1,000 pounds. Let's take a look at its maiden voyage. This is first flight earlier this year. It's a beautiful aircraft. Designed to fly for months at a time, a constellation of these will eventually provide the internet backbone we need for suburban areas. Rather than laying cables over the ground over long distance, we simply build the backbone in the sky. For urban networks, the key is wireless. We're setting records with Ares, our cellular solution for high-density cellular data networks, and Telegraph is a gigabit-scale backbone solution on the right that we're testing on the Facebook campus and testing soon in the city of San Jose. But the best part about all of this is because we're trying to spread this to the world, all of this technology is being opened in the Open Compute project and the Telecom Infrastructure project. So companies across the industry can collaborate together to accelerate the development and deployment of all of this technology with one simple goal: dramatically reduce the cost of providing internet access to people all over the world. That's connectivity. Next up, artificial intelligence. Building intelligent machines has fascinated humanity since the beginning of time. The Turk automaton was a ruse developed in the 1700s, claimed to be a chess-playing machine. It was really a chess master hiding under the table. In the 1990s, this is what state-of-the-art computer vision and AI look like. This is Jan LeCun. He runs the Facebook AI Research Lab. Here he is at the time in his lab in AT&T Bell Labs, and he's pioneering some of the core techniques that are powering AI today. Let's see him at work. What he's built here is an optical character recognition system. That's his phone number, handwritten, and he's built a computer system to scan it. Pushes a button, sees the digits read out. Now, this seems pretty basic to us 2 or 3 decades later, but what he's done is laid the foundation of algorithms, convolutional neural nets, deep neural nets, that are powering today's revolution in AI. So you may say, well, if we had the ideas back then, why didn't we have the AI revolution we have now back in the 1990s? And the key was we needed core technology to catch up. In this case, computational power has increased dramatically in the 2 decades in between. We've seen a 10 to the 6 orders of magnitude, 1 million time increase in computational power. We also seen a massive increase in the amount of data we can use to train these systems. Just on the Facebook networks alone, we're seeing 2 billion photos shared every single day. And so you put these together, and you have, as of 2013, a revolution in computer vision. Traditional computer vision techniques made way to application of these generic convolutional neural nets that can learn based on training data. So let's add an image here. And in 2013, the computer vision state-of-the-art could detect a little bit of information about this. We're trying to teach computers how to see. And this is what the computer would say. There's 3 people in this photo, and they're about in this region. Anyone guess, based on this data, what this photo's about? Anyone? No idea, right? State-of-the-art 2013 computer vision, pretty cool, still not useful. Let's move the clocks forward and see how AI has progressed. So we go to 2014, we get much sharper masks. 2015 and 16, we get much better labels on the data. As of 2016, we can even get skeletal pose, so we know exactly how people are arranged. And based on this, you'd have a much better chance of guessing what this photo is, which is an iconic photo of a protest in Baton Rouge, Louisiana, earlier this year. And so computer vision has gotten to the point where it's useful for real-world applications. Every day, any one of the 2 billion photos uploaded to Facebook can be instantaneously captioned in a way like this by a computer for anyone who wants to read it. So if you happen to be one of the hundreds of millions of people around the world with a visual disability, you can also participate in the visual world of Facebook through the power of AI. Watching computers label images like this is one of the things that I think gets people excited about AI and also gets them overexcited. Because they say, oh my gosh, if it can do this, it understands things. We are years away from human-level computer AI. But I'm here to tell you that's not true. Here's the same systems on a different set of images. Plausible sounding caption? I wouldn't say that plane is parked, would you? So if you know nothing about AI, I can give you the 30-second master class on how this is working. We take a set of training images. We label them, have people label them. And you can think about a set of airplane images, where airplanes are generally in the sky, and generally when they're on the ground, they're probably at the airport, right? Parked on the tarmac. We train all these images into the system. It builds a statistical model. And then it looks at a set of pixels, compares it against that model. So you can imagine that training set didn't have any plane crashes in it. The closest thing it had was a plane parked at the airport. So that's what it guessed. This gives you a clue that these systems are cool and useful, but not truly intelligent. Let's take it another step further. For everyone in the audience, is this a vegetarian pizza? No, right? It's got sausage on it. Sausage is made out of meat. Vegetarian means you don't eat meat, right? Think for a moment. When did you learn what vegetarianism was? Was it this morning? This year? A decade ago? For me, it was several decades ago. So everyone in this room, tens of thousands of people, instantaneously pulled a random fact out of your brain to answer this question. There's no chance you studied up on vegetarianism for my talk, right? CTO of Facebook, I'm going to read about eating patterns. I doubt it, right? That is a measure of true intelligence. And by that measure, our existing AI systems are pretty darn basic. And we prove this a different way by building a very simple set of tests. This is a 20-question set of tests to test for intelligence in machines. And when we proposed them just a little over a year and a half ago, no existing AI system could solve these problems. These are simple word problems where we have a couple sentences and a question, and the answer is right there. You just got to find it. Over the intervening years, the research community has come up with solutions for many of these problems. And before this talk, I would have said 19 out of 20 of these questions were solvable. But breaking news, as of Friday, our research teams submitted a new paper that shows a system that can answer all 20 of these questions. So we're making progress. But again, by human measures, we're still very, very basic systems. Another way to think of this is the idea of taking Wikipedia, a Wikipedia article about, say, a movie, The Matrix, and trying to answer complex questions out of that text. If we could build systems that could do this, we could build truly intelligent machines that are helpful for us. This is the frontier of current AI. But the other fun thing about AI is, like humans, it can be used not just for knowledge. We're not just fact machines. We're creative, right? We like to do new things, create art. And so the same neural nets that can be used to answer information can help us create. This is a system called style transfer, where you take a source image and you paint its style onto any other image you want. In this case, The Simpsons, could be Van Gogh or Picasso. And this is a really good example of the pace of progress of AI. The first paper on this was written August 2015. Required a big, beefy machine and was pretty slow. 6 months later, the research community had a new technique, 3 orders of magnitude faster, 1,000 times faster. Our engineers said, maybe we can get this to work on your mobile phone, so you can do it in real time rather than having to send it to a server farm. The first version of that didn't run terribly fast, ran about a frame per second. Just a few months later, we have this running in real time on a modern cell phone. This means you can be recording a video and have it painted with whatever style you want from any source image. This, in about a year's time, is 5 orders of magnitude faster. Rapid progress. To show you this in work, this is a video we took here in Lisbon. And as we're recording the video, we're painting it with a variety of different styles. This is a live neural net running on device, running about 30 frames per second. And so this means I can see immediately, do I like this or not, before I post it, rather than having to wait for the server to process. And this is one application of AI on the device. It's one of the first. But the real breakthrough here is being able to train and build models on a big server, and then take those models and deploy them directly to your pocket so that you can run them in real time wherever you are. That is the exciting future of AI. All right, let's wrap up, talk about VR. VR is another area that has fascinated humanity for a long time. The idea of augmenting your senses and giving you a sense of presence somewhere else. But it's here. You can walk into a store today and buy a VR headset. And so one of the questions I often get on VR is, if we've been excited about it for so long and previous attempts have failed, why is 2016 the year that VR is actually going to work? And here's one really good reason why. Like AI, we needed to wait for all the component technologies to catch up to us. This is state-of-the-art graphics in video games circa 1980. You wouldn't look very real in this in VR, but you can see the rapid march of progress. And if you look at 1980 versus a PC or console in 2016, you can see we can start to build this sense of immersion in VR. And one of the most fun demos to give is this demo where you're in this great sci-fi landscape. You're looking around, there's a cool blimp over to the left, some spotlights. Then we might tell you, go ahead and look down. And you look down, and you realize you're right up to the edge of a building. And I love giving this demo, because what I try to do is say, keep going, keep walking while you're at the end of this ledge. And it's amazing to see people lock up, and they just can't do it. And they were 30 seconds ago in a conference room. So they know in their rational brain there's no way they're on top of this building. But VR has gotten powerful enough to give them that sense of presence. And this sense of presence works in the real world, too. When you couple it with camera capture, you can transport people to real-world experiences. This is Clouds over Sidra. It's an amazing video about life in a refugee camp. And UNICEF credits this video with helping people understand what that is like and helping them raise 70% more than expected, or $3.8 billion. So it gives you that sense of presence. And VR has had applications I would have never dreamed of. This is the Walk Again project in São Paulo, Brazil. These researchers have done some of the most amazing work I have ever seen. They took VR, Oculus Rift, brain-machine interfaces, and robotics. They've taken patients with severe spinal cord injuries, fully paralyzed. They've put them into VR and simulated like they were walking. You can see them simulating that they're moving their legs. So the same thing that gave you the fear of standing on a building can help retrain your body to reactivate, they think, neurons that weren't damaged. And what you're seeing is patients who didn't respond to any prior treatment restoring partial motor control. This is stunning work. Credit goes to them for doing all the hard work here. And so what we're focused is, how do we get VR to the whole world? This is one of many, I think, foundational applications of VR for the world. So our part in this is, how do we make this technology cheaper, easier to use, and more widely distributed? One of the challenges of VR is you either need a big PC and a lot of money, or you can do a mobile VR system that you can carry with you and use on your mobile phone, but it doesn't have all the features of that big VR system. And that's why we're so excited about R&D in a new area, a new product called Standalone. The idea is it's a VR system that's all combined. You just pick it up off the table, put it on, you're in VR. No PC needed, no external equipment needed, no special room. Here's a little teaser video of this in action. You'll see he'll put it on. It has everything needed to go into VR. And what's amazing is it's using state-of-the-art computer vision, AI algorithms, to use cameras on board to track his position. So as he's moving in the real world, you'll see the virtual world move around. You'll see he'll bend over this railing here. As he does it, the headset is perfectly tracking his position. So it gives you that true sense of immersion. No PC required, no cables, nothing. This is the product. It's an early prototype, not on the market yet, but it's this sort of technology we think will eventually bring VR to the masses. But everything I've showed you today is passive consumption. This gets really fun when you interact. This is Touch, our hand controllers, shipping later this year. And this is an early prototype we built called Toy Box. And this shows you the real world on the right and the virtual world on the left. And you can see how quickly and easily it maps your hand motions. It's difficult to perceive any difference between the virtual world and the real world. So this gives you an amazing sense of presence of your hands and a chance to see someone else in VR. And so we knew we were onto something in terms of this idea of social VR, presence in VR. And so we showed a new version of this system called Social VR earlier this year. Just a short number of months ago, Mark Zuckerberg stood on stage and had a conversation with some of our colleagues. That's Mike Booth and Lucy Bradshaw. Here's a clip of them. This is Mike Booth backstage here on the left in the real world, and this is his avatar in VR. Notice how expressive, how realistic. They can play cards. They're going to goof off a little bit. Can draw and create in VR. And you can even portal into the real world. This is Priscilla Chan, Mark's wife. She was doing rounds at the hospital, but able to video chat in via Facebook Messenger. And she and Mark and their dog Beast took a nice little selfie in VR. This is the future. The ability to connect with the people you care about, even if they're dozens or hundreds or thousands of miles away. That's why we, Facebook, are so excited about VR, because it is the technology that's going to enable this deep social connection over long distances. That's why I'm so excited about the future. Thank you very much, everyone. It was great to see you at Web Summit.